Doc, the Physics of Sound and Music, Lab 9 review. Looks like only four things here, four lines. First, give the Fourier amplitudes for the sine, triangle, square, ramp, and pulse train waveforms. Now, we've looked at that in our course a few times and memorized it a few times, doing a refresh on our memory. Let's do that again. Draw these in terms of the simplest one, the most elegant one in terms of simplicity, the sine wave. And then notice that the triangle is close to the sine wave, but a little different. And the square is more different. And the ramp is even more so, where you now break the symmetry of up, down, up and down like this, where you can do a reflection. Here you have a ramp up and you come straight down and go up again, straight down, go up again. And this one here is most trying on your eardrum because it says push your eardrum in rapidly and then rapidly pull it out and then rest it and then push it in and out. So this is easy on the eardrum, nice periodic wave that's harmonic. And then this a little different, and this brings in the upper partials, the other components, when you use the Fourier idea of breaking these down into their component parts where you have sine waves. This is the first harmonic, the second, the third, the fourth, and the fifth. So with the sine wave, you just have the first harmonic and nothing else. For the pulse train, you have everything. And then for the ramp, you sculpt things so you have one half, one third, one fourth, one fifth, one sixth. For the square, you kill the evens, put the zeros there. And then to get the triangle, you square the square. So 1 times 1, 3 times 3 is 9, 5 times 5. And that then gets us the memorization of all of those. The richest one being the pulse train in terms of Fourier spectrum, and the simplest being the sine wave. What is plotted on the vertical and horizontal axis in the time domain, frequency domain? And for that, we go here to 914. And in 914, we have our sound segment. That's your oscilloscope, where you have time along this axis. Here you have centiseconds, but you can simply rip off the decimal points, throw away any zeros to the left, and have 2, 4, 6, 8, 10, 12, 14, 16 milliseconds, which is what we use in our class more often than the centiseconds. This would be your volts or your amplitude. Usually it's volts. And then for the sound spectrum, that's your Fourier spectrum, where you have your harmonic frequencies here. These are the frequencies, but your harmonics would be, for example, if the first harmonic's 0.5, then first harmonic would be there, second would be there, third would be there. So think of these as frequencies, but with the idea for periodic waves to put a bar graph down to give you the amplitudes of the various harmonics. But when you have a general wave, it may be more complicated, most time as it is, and your inharmonic sounds have all kinds of stuff in between the harmonics. So that takes care of the two domains. And how do you convert kilohertz to hertz? Well, whenever you have kilohertz, a kilo means 1,000, so 3 kilohertz would be then 3,000 hertz, and vice versa. Think of a kilohertz as like a kilo buck, like imagine $1,000 bill. Then if you had like $3,000, well, there'd be three bills, so it'd be 3 kilo bucks or 3 kilohertz, say, in the analogy with the frequency. Milliseconds, these are tiny. Milli means 1,000th with the th on the end. So if you have 1,000 seconds, that would be, well, I didn't mean to give that example. That's actually 1,000,000 milliseconds, because you have to have 1,000 times whatever you got for seconds to get millis. I meant to say 1 second. If you have 1 second, then you have 1,000 millis. But if you did have 1,000 seconds, it'd be 1,000 times 1,000, which is a million milliseconds. If you want to go the other way, say you have 500 milliseconds, see, then you divide by 1,000, and that's a half a second. So pick some numbers, go both ways, get some practice with those. Inharmonic spectrum, that's your more typical spectrum, would be have things in between the harmonics. So that means you have things in addition to your harmonics. It's inharmonic. And some examples, well, pretty much, I mean, a lot of examples here. I mean, gong sounds, me talking, for example. Unless I'm singing a pitch, it's going to be an inharmonic sound. So I think that's a little review there for the Fourier synthesis. And the bar graphs, though, are nice to look at for a second. Let's just go ahead and find some of those. It'd be nice to see. Yeah, here you go. This is a nice example where you see a picture of the wave in the time domain where you have the amplitude, and this is time, and then the frequency domain you have your Fourier spectrum idea. And here we can play around clicking these buttons and see how things change. What we're doing here is we're taking harmonics away. Put the first one in, and here I'm going to take away harmonics. And here when you have your so it was a square wave, that's odd harmonics, and here, down in here, let's see, this doesn't seem to be working here. This should be changing down in here. Oh, I see what it's doing. It's going blue. Alright, so the blue means it's not there. Okay, that's cute. So what they're doing there is just saying if it's blue, you know, it's not really there. So I just have that red one, that's the sine wave, that's this one here. And then if I bring in my odd harmonics, I start to make my sine wave, and then these blue ones become red, and that means they're really there. Well, that's the review for Lab 9.